So let's go ahead now and we'll derive the potential energy for a double pendulum. And once we've derived that, we'll take the potential energy away from the kinetic energy and we'll get the final Lagrangian which we're interested in. So the potential energy is an energy of position, and in this case the position is the surface of the Earth. So we can use the simple formula potential energy equals mass times gravity times the height. So we've got the potential energy of the mass m1, so that's going to be given by m1 times g times y1, and the potential energy of mass m2 given by m2g y2. Now have a look back at the original drawing and ensure you remember and understand the distance y1 and the distance y2. So we can take out this common factor g, so this is just the acceleration due to gravity near the surface of the Earth. So it's going to be g m1y1 plus m2y2. Now we can substitute the y1 and the y2 values in. So y1 from a previous video is minus L1 cos theta 1, and the y2 is minus L1 cos theta 1 minus L2 cos theta 2. We can then take out the negative sign from each of these, so it's going to give us minus g m1 L1 cos theta 1 plus m2 L1 cos theta 1 plus m2 L2 cos theta 2. We can take the common factor of the m1 m2, which is going to be the L1 cos theta 1 here, so we've taken that out here, and we've got minus g m1 plus m2 L1 cos theta 1 plus m2 L2 cos theta 2. So this equation here is the potential energy of our double pendulum. So now what we can do is we can take the potential energy U away from the kinetic energy T, and we'll get the Lagrangian. So the Lagrangian is going to be given by this equation here. So the first part of the equation we derived in a previous video, and that's the kinetic energy of the double pendulum. And the second part we've just derived here, which is the potential energy of the double pendulum. And note it's T minus U, so the minus cancels with the minus and gives us our plus sign here. So let's go ahead now and we'll see how we can apply the calculus of variations to this particular Lagrangian. So we've just derived this quantity that gets minimized, and we've called it the Lagrangian, which is the kinetic energy minus the potential energy. So we can apply the calculus of variations to this quantity. Now I've rewritten the Euler-Lagrange equation here, and I've written it in terms of the generalized coordinates. So if you like, these are the degrees of freedom. So the 1 degree of freedom is the angle theta 1, and another degree of freedom is the angle theta 2. So we can write d by dt partial L by partial qi dot minus partial L by partial qi is equal to 0. But we're going to end up with two lots of these Euler-Lagrange equations, one for this degree of freedom here and one for this degree of freedom. So we're going to end up with the Euler-Lagrange for theta 1 and the Euler-Lagrange for theta 2, and we're going to have to put this equation here L into this one, and we're going to have to put equation L into this one, and in this one here we're going to be differentiating with respect to theta 1 dot and theta 1, and this one here we're going to be differentiating with respect to theta 2 dot and theta 2. So let's go ahead in the next video and we'll start doing the calculus of variations on this Lagrangian.